Okay. So magnetic fields are produced by moving charges. Okay. They're also produced by time-varying electric fields, but this is all we're studying in this chapter. Okay. And so here was the fundamental process. Now this is a classical approximation, but okay, so if you have a moving charge like this, so we're considering a positive charge. If it's moving like that, at that point, the field produces, so what you do is, if it's moving in this direction, if a charge is moving in this direction, you draw cylinders around the axis. This is the axis of the cylinder. You draw cylinders around, and the magnetic field is tangential to the cylinder. Okay? And the sense is as follows. You use your right hand, point your thumb in the direction of the motion of the charge, and your fingers point in the direction of the magnetic field. Okay? So the magnetic field points like that. And also, the further out you are from the charge, the weaker the field gets. Okay? So that's how the fields are produced. So these moving charges produce that field. Okay, so that's the configuration. What this diagram shows you is, okay, so if the charge was going into the plane of the paper, so this is showing you an end-on view. If the charge was moving into the plane of the paper, the magnetic fields are in that sense. Okay. All right, so here's the formula again. There is the charge moving in that direction, and mu naught is a constant. It's the vacuum permeability, mu naught over 4 pi. Q is the magnitude of the charge. V is the velocity. R hat is the unit vector pointing in the direction pointing in the direction of the point at which you're finding the magnetic field. That's R hat. And the strength of the magnetic field is inversely proportional to the distance squared. Okay, so if you're twice as far, the field is 4 times as weak. Okay, that's what that means. All right, so let's see. Okay, what if this was a negative charge moving in this direction? Which way would the field be? Exactly. The field would be in the opposite direction. Very good. Okay? All right. Now, we also saw that now if you have so this is the field produced by a single charge. If you have a current is a whole bunch of charges moving in that direction. Okay? And each would produce a field coming out of the plane of the sheet. So the field of all those charges would add up. Okay? And the field at this location would point like that. And that field, okay, is given by, again, exactly the same expression, except that QV got replaced by IDS. Okay? I is the current in the wire, and DS is the element, that small element of wire that's producing that magnetic field. And if you wanted the magnetic field due to the entire wire, you would add up all those elements, all those contributions. And that's that integral. Okay? We saw all of this last time. So ds cross r hat divided by r square is that expression. That's the magnetic field produced by this element. And if you have a long wire like this, you would sum over all contributions due to all those elements, and that's an integral. Yep. And we said that in general this integral is not easy to do, or for a wire like this, if the wire was like this and you wanted to calculate the magnetic field of this wire at that point, this integral would be impossible to do. Okay? You couldn't do it analytically. So when can you do the integral if you wanted to find this, the magnetic field at that point? When is it possible to do this integral? When the line is straight is one instance. Okay? And if it was a circular wire, you could do the integral when the point was on the axis. Okay? So for an infinitely long straight wire, you could do the integral. For a circular wire, you could do the integral for points along the axis and so on. So you can do this integral in very special cases. All right. But in principle, you have the expression for it. Okay. So what does this give you? It tells you how to calculate the magnetic field at various points due to a current carrying conductor. Yep. So here is the field due to a straight, infinitely long straight wire carrying a current I. And again, the magnetic field lines are concentric circles around this conductor. So the field lines are tangent to the circles. And the further out you are, the weaker it gets. So the magnetic field is mu naught I divided by 2 pi A. A is the distance from the wire. Okay. Now this shows you the field due to a circular current. Okay. So for instance, you can have a battery like that, and of course there would be a cut in the wire there. So here's a current flowing like that. Okay. And so when you close the switch, you would produce a magnetic field like this. And this magnetic field looks like exactly like the magnetic field of a bar magnet. Okay. And this is called an electromagnet. And as we saw, the advantage of this is you can change the strength of the magnet by changing the current. You want a stronger magnet, you just pass a larger current. Okay? And by the way, you need a resistor in there. You pass a larger current. And the advantage is you can switch this magnet on and off. Okay? So this is called an electromagnet. It's a very useful device. Okay. So I said this integral can be done in very special cases. So for instance, if you have a circular current for points along the axis, you can do this integral. And here's somebody has done that integral for you, and here's the expression for the magnetic field. Okay, so the magnetic field along the z-axis along the axis of the ring is given by that. Okay, r is the radius of the ring, z is the z coordinate. Okay, so that's the magnetic field on the axial points. And again, if you wanted the expression for this point, if you wanted the magnetic field at this point, well, you're out of luck. Okay, that integral is we can't do that integral. So this is also showing you, so this expression, what this page is showing you is, okay, for various values of z. It's plotting the magnitude of B for various values of z. Okay, here we're calling that coordinate x. So here is the ring, and there's the center of the ring. It's carrying a current like that. And the magnitude of the magnetic field along x is given by this. At the center of the ring, the magnetic field is maximum, and as you go along the x-axis, the magnetic field falls off fairly quickly. Okay, and the magnetic field falls off as 1 over x cubed. What is a current carrying ring? What is this thing called? What is this? It's an electromagnet, and the electromagnet, the strength of the magnet is given by the magnetic moment, and so the magnet points in this direction. So the magnet points like that. Okay, so that's the direction of mu. And again, you use your right hand, point your fingers in the direction of the current, and your thumb points in the direction of the magnet, of the magnetic moment. And the strength of this moment is N, the number of turns in the coil, times I, the current, times the area of the coil. Okay, and if it's a circular coil, the area, of course, will be pi r squared. Okay. All right. what this is showing you is if you have two parallel wires and they carry current in the same direction, they'll attract each other. Okay. So, well, what is happening? Okay, this wire is producing a magnetic field all around it. In particular, it's producing a magnetic field at the location of this wire. Okay? And when this wire carries a current, it has moving charges, and those moving charges feel a force in the presence of this magnetic field. And the force they feel is V cross Q, is QV cross B, which is V cross B. If you turn a screw from here to there, the force will be in that direction. All right, so wires carrying parallel currents feel an attractive force. If the currents are in the opposite direction, the force would be repulsive. Okay? So force per unit length is given by that. Okay? And again, there is a force if both the wires are carrying currents. If one of the wires is, the current is zero, there is no force between them. Okay? So, all right, so there is the force per unit length. And again, this expression would, so if one wire were going in this direction, another wire is going in this direction, this expression would not work. Okay, so they have to be parallel. Okay, what Ampere's law is the following. So if you go back to one of the first chapters for electrostatics, you had, let's say you had a surface like this. This was the electric field, and there was the area element, dA. Okay, so Gauss's law said the flux for an enclosed surface EdA. Okay, so this was a surface integral, and that circle denoted it was a closed surface. Okay, so Gauss's law said for a closed surface, the surface integral, the flux is given by the charge inside divided by epsilon naught. Okay. The parallel of that is Ampere's law. So now, here it's a line integral. This is a surface integral. So this is a line integral. So the line integral around a closed loop, okay, of the magnetic field is equal to mu naught times the current threading that loop. Okay, whatever is the current inside the loop. So all these currents are producing a magnetic field all around them. Okay, and you can do any loop, draw any loop, take the line integral of that loop, okay, and that the value of that line integral would be equal to mu naught times the total current threading that loop. Okay, and if you're going in the loop in this direction, again you use your right hand, your fingers are pointing in the direction of the in which you traverse the loop, your thumb points in the direction of positive currents. So these currents would be positive and that would be negative. Okay. So for instance, if you did the line integral around that loop, there's no current threading that, so that line integral would be zero. Okay. Okay, what this is showing you is, so here's a thick wire, and if it's carrying a current distributed uniformly and throughout the wire, and the current is coming out of the plane, so the current is coming. These are the magnetic fields. So the magnetic field at the center would be zero, and you see as you go outside, the strength of the magnetic field is increasing. And the magnetic field is strongest at the surface of the wire. And then once you're outside the wire, the field strength decreases. Okay, and that's what this graph is showing you. So the magnetic field strength for R less than zero increases linearly with R. Okay, so inside the wire, the strength is increasing linearly with R. Okay, it's maximum at the surface, and then once you go out, the strength is decreasing. Okay, and if you're infinitely far away from the wire, R is infinity, the magnetic field strength would go to zero. Okay. Again, what is happening is you point your thumb, okay, so if the the current is coming out of the paper, the direction of the magnetic field is as your fingers point on the right hand, okay? Now here's a very important magnetic field configuration, okay? So you can take a donut and wrap wires around it, okay? And now if you pass a current through this thing, you'll get a field inside the donut that's, so the field lines are circular. Why is this important? You guys remember, so let me draw a field line. So what this indicates is magnetic fields going into the sheet of the paper. And you guys remember, if you, let's say you throw a charged particle like that. So let's say you throw a charged particle like this. Okay, so this V cross B is into the plane. V cross B would be a force in that direction. So this guy would feel a force in that direction, okay? The force on that will be like that. And so what this charged particle does is it goes in a circle, okay? So field lines, magnetic field lines trap moving charged particles. The particles go wrap around the field lines, okay? And of course, so if this is the field line, okay, so if the particle has a component parallel to the field line, it'll get trapped like that. It'll make spiral motions, okay? Now, if you have charged particles, if you have very hot charged particles, but they get trapped on the field lines, they'll just go in circles like that and never hit the walls of the donut, okay? And that is used in fusion reactors, and we've seen images of this several times. The tokamak, okay? And that's right, okay? And actually, so that's a national lab, and Princeton University has a tokamak. And they have, what do you call them? They open it to the public sometime in April if you guys want to go to check it out. Or if you're in that area. Okay. So there you go. So this is plasma, and those are the field lines. And this plasma could be at millions of degrees. Okay, and if it hit the walls would vaporize instantly. Okay, so they never hit the walls because they're going around the field lines. Okay, and that's the toroidal magnetic field. So, see, this is the toroidal magnetic field. It's going in circles around. Okay. All right, there's other configurations. So you could, of magnetic fields, you could take a cylinder, okay, and wrap wires around the cylinder and pass a current like that. And what this does is it produces a strong field inside the solenoid. And so this is the field, and the field here is 0. Outside the solenoid is 0. And inside the solenoid, it's nice and strong. It's strong and uniform. So for instance, inside an MRI machine, this is the field. You need a field like this, and you put the patient there. Okay? And so that's what this is. So now, if you take a cross-section like this, okay, this is showing you a cross-section of the solenoid. So this is the wire is wrapped around like this. It's coming out of the sheet and going in there. So current is coming out and going in like that, and going out, coming, okay? And here is the uniform magnetic field. Yep. And the strength of this magnetic field is mu naught times N. N is the number of wires per meter, okay, times I. N is the number of windings per meter, okay. The expression for the solenoid is the same, okay. The magnetic field strength inside the solenoid is mu naught N, the number of windings, times I, the current, okay. All right, so the expression is the same in both these cases. Okay. So you guys know this lab in Europe, the Large Hadron Collider. Okay. So you see this, the detectors are filled. So this thing is filled with detectors, particle detectors. And UF has a lab that builds some of these detectors. And the circumference of that ring is about 60 kilometers. Okay. So there's the Large Hadron Collider. Okay. And let's see where the detectors placed. Okay, so they placed those detectors so there, and they place the detectors at various locations. Okay, so they'll make a beam of proton and a proton beam collide at the detector, and here's what they do. So this is a solenoid. There's wires around it that wind around the solenoid, and you pass a current through it. What does the solenoid do? It produces a uniform field inside the solenoid, just like that, okay? So there's the cylinder, you wound wire around it, passing current through the wire, and it's producing a uniform magnetic field through it, okay? And you pack this whole thing with particle detectors, okay? So when this is all packed, so that's where the beam is coming through, proton beam, and there's a opening in the other side, on this side, so the proton beams come and collide in the middle of the detector. And look at this. When two protons collide, okay, these are particle-antiparticle pairs. Okay, so the energy is used to create particle-antiparticle pairs, and the magnetic field is bending these particles. The lighter the particle, the more they bend. Okay, so from the curvature of the particle, they can calculate the mass of the particle. Okay. Now, if they collide two gold nuclei, there's a lot more debris. Okay, a lot more stuff is created. This is proton beams colliding, and these are the tracks. Okay. All right. So what does this chapter has taught you? That moving charges create magnetic fields. Okay. So now we'll look at this at a microscopic level. So in an atom, you have electrons moving around the nucleus. Okay. So these are moving charges, and these will produce magnetic fields. Okay. So you saw that a ring of current. What was this? A ring of current behaved like a magnet. Okay. And the strength of the magnet which is the magnetic moment, was given by N times I times A. N is the number of turns of coils you have. Okay. So if an electron is going in an orbit like this, that's like a current, except that it's current in the opposite direction. Okay. And so this should behave like a magnet, and there is the magnet. Okay. And the strength of this magnet is given by that expression. I times A area, because it's only one loop. I is the current, A is the area of this loop. Okay, and so if you do the model of the atom, all that expression works out to this. L is the orbital angular momentum. Okay, so the strength of the magnet is given by E given by this expression. Okay, so that's the strength of the magnet. Okay. In chemistry, you learned this. So for L equal to 0, so L can take all these integer values. Okay. L equal to 0 corresponds to the s orbital. L equal to 1 corresponds to the p orbital. This is d, f, and so on. All right, so you see that in the s orbital, there's the s orbital, you can think of the electrons, it's not going in circles, but it's going through the nucleus. And so it's not acting like a magnet. Okay. Only p orbitals and so on have magnetic moments. Okay. P and higher orbitals. Okay. So again, an electron going around in the nucleus of an atom has a magnetic moment associated with it. Now here's the amazing fact. In an atom, each electron circles the nuclei once in about 10 to the minus 16 seconds. So an electron will go around the nucleus in 10 to the minus 16 seconds. This corresponds to a current of 1.6 milliamps. And this should produce a field of 20 Tesla at the center of the atom. 20 Tesla is a very strong magnetic field. It's 10 times stronger than the MRI magnetic field. So why aren't all atoms very strong magnets? No. If an atom was sitting here and it produced a 20 Tesla magnetic field, any gurney in this room would jump towards the atom. So in general, what happens is for every electron going like that, there's another electron going in the opposite direction. Okay, so the magnetic moment of that gets canceled by the magnetic moment of that. And for the odd number of atoms with odd number of electrons, the last electrons is in an s orbital, and the s orbital, the magnetic moment is 0. Okay, so the orbital motion contribution is generally 0 in all atoms. Okay. In most materials, because of oppositely moving electrons, magnetic effects produced by orbital motion is 0 or very small. Okay. But electrons spin as well, and so that's moving charge, and they act like magnets. Okay. So a spinning electron acts like a magnet, and there's the magnetic moment is pointing in that direction. And again, the magnetic moment like that, you can think of it as North Pole there, South Pole there. Okay. So there's the magnetic moment. Okay. And well, how strong is this magnet? A spinning electron. The strength of the magnet is given by that. This is called a Bohr magneton. Okay. It's given a special name after Mr. Bohr. And the strength of the magnet is 9.27 times 10 to the minus 24 joules per Tesla.
What is that H next to the E?
Oh, that's Planck's constant. So H bar is H divided by 2 pi, and this is Planck's constant. Yeah. Yep. So again, what is this number?
It's the spin of the electron, or the magnetic moment.
Of the spinning electron. Every electron is spinning at the same rate, and that's the strength of the magnet. Okay. Look at that number closely. 9.27 times 10 to the minus 24. Okay. Here is the hydrogen atom. There is its magnetic moment. So the hydrogen atom is a proton and an electron. An electron in the s orbital. So the s orbital has zero magnetic moment because it's really not going around like that. But it's spinning. The electron is spinning, which acts like a magnet. And so the magnetic moment of the entire atom is essentially the magnetic moment of the spinning electron. You guys see that? That's the magnetic moment of the spinning electron. And there's the magnetic moment of the hydrogen atom, which is that. Well, the proton is also spinning, and the proton is acting like a magnet as well, just like the electron, except that the strength of this moment is about 1,000 times less than that. So you can ignore this moment. So the moment of the hydrogen atom is just that of the spinning electron. Okay? And this gives you various magnetic moments of various ions. So cesium 3 plus ion, it's twice that, meaning you have two electrons in parallel configurations. The two spins of electrons add up. Okay. Atoms with odd number of electrons generally have non-vanishing moments. Magnetic moments of an atom is the vector sum of spin and orbital angular magnetic moments. Okay. All right, I'm going to quickly describe some magnetic materials. If you're a material science guy, you'll run into this stuff. And magnetic materials are important because we've used them for storage and stuff like that. Okay. So substances are classified as ferromagnetic, paramagnetic, or diamagnetic based on their magnetic properties. Paramagnetic and ferromagnetic materials have atoms with permanent magnetic moments. So these materials, their atoms have magnetic moments. Okay. Here's paramagnetic, here's ferromagnetic. This is anti-ferromagnetic. You see, you have domains that have opposite magnetization. Okay. And again, these are specialized. Ferrimagnetism, the opposite is smaller than that. Okay, so there's a net magnetization in this direction. Diamagnetic materials are those made of atoms that do not have magnetic moments. Okay, so these guys have magnetic moments, these guys don't have magnetic moments. All right, ferromagnetism are materials that you can make strong magnets out of them. So cobalt, iron, and all that, those are examples. Okay. In ferromagnetism, each atom is a magnet. And you see what this is showing you is this is the size of a small grain of sand. And this is called a domain. And in this domain, there are about 10 to the 20 atoms. And all those magnetic moments of the atom, all those individual atoms are aligned. But look at this next grain, they're aligned, but that magnetism is pointing in that direction. So what do you think is the net magnetism of this bulk sample? Zero. So here is a material whose individual atoms are magnetic, and they even collude to that level, and their magnetism is aligned. But for a bulk sample, this magnetism is zero. Well, if you want to make a strong magnet out of this, what you have to do is align all the domains. Okay, well, how do you align all the domains? So what you do is you take this material, there's random magnetization, you wrap a wire around it and pass a current through it, and that current will produce a magnetic field inside which will align all the magnets. Okay, so using a current you can make a strong magnet. Okay? And then if you're tired of this guy and you want to get rid of it, of course you can pass an AC current and randomize it again, or take it and hammer it and hit it on the ground and it'll randomize again. Okay, anyway, ferromagnets have these domains, and these guys within a domain, all the magnets are aligned. Okay, how large are the domains? Roughly the size of a grain of sand. Okay. Okay, let's see. Magnetic moment per unit volume of a substance is called magnetization. Okay. For paramagnetic, okay, so again, you saw that if you introduce a magnetic field, these moments will align. Okay, so for a paramagnetic material, the moment is proportional to this field strength. Okay. For paramagnetic and diamagnetic substances, magnetization is proportional to the magnetic field strength. Okay, so the net field, so here's an external field, and then when you magnetize, the field will increase. Okay, inside the substance, the field will increase. Okay, and the field inside is the applied field times plus a term due to magnetization. Okay, and we define something called magnetic field strength denoted by H. Okay, mu naught times H is B. Okay, and the magnetization is proportional to the field strength. This is called the magnetic susceptibility, chi. Okay, that is magnetic susceptibility. For paramagnetic substances, magnetic susceptibility is positive. For diamagnetic substances, magnetic susceptibility is negative. What this positive means is if you apply an external field, the magnetic moment in the material line up. So this chi is positive. For diamagnetic materials, you apply a field, and the magnets in the material line up in the opposite direction. Okay, and chi is negative. Paramagnetic substances have small but positive magnetic susceptibility because of atoms with permanent moments. These moments are weakly interacting, and in the absence of external fields are randomly oriented. In ferromagnetic materials, they're strongly interacting and they'll line up. In a paramagnetic material, even though individual atoms are magnets, they won't line up like this. Okay, so you can't make a strong magnet out of them. That's what this statement is saying. Okay. Water happens to be diamagnetic. Okay, so what this is showing, so if you put a water molecule in a magnetic field, its magnetic moment will be in the opposite direction of the magnet. Okay, and so if you have a strong magnetic field, you can make a water droplet float. Okay, and what this is showing you is they froze this frog, and they have applied a magnetic field like this, and this frog is floating in air. Okay. And apparently, so shown as a frog levitated due to a diamagnetic force by a 16 Tesla magnetic field. Okay, so you need a very strong field to do this kind of stuff. Okay. Here's a superconducting magnet, and or this is the superconducting magnet. This is an ordinary magnet, and this is acting like a diamagnet. Okay, and it's floating. All right. Okay, so those are the concepts from this chapter.